I'll be explaining another important approach for contrastive learning of unsupervised sentence representation. So, contrastive learning has been shown to be effective in improving pre-trained language models to derive high-quality sentence representation. It aims to pull close positive examples to enhance the alignment while push apart irrelevant negatives for the uniformity of the whole representation space. However, previous works mostly adopting batch negatives or sample form training data at random. Such a way may cause the sampling bias that improper negatives are used to learn sentence representations, which will hurt the uniformity of the representation space. We present a new framework, this debiased contrastive learning, to alleviate the influence of these improper negatives. So they designed an instance weighting method to punish false negatives and generate noise-based negative to guarantee uniformity of the representation. So we have two measures. One of them is uniformity, the other one is alignment. We use this to see if our contrastive learning is working properly and avoiding the collapse, either full collapse or dimensional collapse. So these are two measures that we use for validation. And as you see, this is a distribution of cosine similarity between an input sentence and some 251 in batch negatives. So what is the problem pre-trained language models? Several studies have found that native sentence representations derived by these pre-trained language models are not uniformly distributed with respect to directions, but instead occupy a narrow cone in the vector space, which largely limits their expressiveness. To address this issue, contrastive learning has been adopted to refine pre-trained language models' derived sentence representations. So it pulls semantically close neighbors together to improve the alignment while pushes apart non-neighbors for the uniformity of the whole representation space. So these are randomly sampled negatives, and we have some input. We give the augmentation as well. And here we have noise-based negatives. So our proposed framework focuses on reducing the influence of sampling bias in the contrastive learning. So they devise a noise-based negative generation strategy to reduce the bias caused by the anisotropy. This is a phenomenon that we have talked before. It causes anisotropy, which it means most of the form are in a particular part. For example, if it is hypersphere, most of the representation are in particular, and even in the feature space, it's just either on a cone or in a particular part of the state space. So we aim to generate new negatives beyond the sentence representation space during the training process to alleviate the sampling bias derived from anisotropy problem. For each input sentence, we first initialize k-random k-noise vectors from a Gaussian distribution as negative representations. So sigma here is the standard variance. Since these vectors are randomly initialized from such a Gaussian distribution, they are uniformly distributed within the whole semantic space. By learning to contrast with these new negatives, it is beneficial for the uniformity of sentence representations. The non-uniformity loss is denoted as the contrastive loss between the noise-based negatives and the positive representation of original sentence. So this tau is just the temperature, it's just a hyperparameter. This tau is just a hyperparameter, we call it temperature, and we optimize by just these t steps gradient ascent. And this beta is just the learning rate. So we utilize the complementary model to produce the weights that we use, that if the similarity between your representation and the negative sample is negative representation is bigger than just the threshold, it could be any hyperparameter, this one, which is just a weight threshold. If similarity is bigger than it's 0, otherwise it's 1. So in this way, the negative that has a higher semantic similarity with the representation of original sentence will be regarded as false negative and will be punished by assigning the weight 0. So we optimize the sentence representations with biased cross-entropy contrastive learning loss. Where tau is the temperature hyperparameter. In our framework, we follow SimCSE that utilizes dropout to augment positive examples. And then this is the uniformity loss of comparing our framework with the SimCSE using BERT-based undervalidation. And the measure that they use is this uniformity loss that is written here. Is just we sample, it's IID, I mean it's identically independent distribution. We sample from that and we see if it is going, during these training steps, you see that it converges to something, but here for the SimCSE, it has a bad uniformity. But for this approach, it has a better uniformity.